Hello my dears, a very good morning to all. So in the last class we discussed some important problems regarding the resonance and series and parallel circuits, especially in parallel circuits. It's very easy to deal with the series circuit, but parallel circuit, you have to think for a while, then only the problem will be in your hand, otherwise it's very difficult. Okay, and the basic idea of resonance, series and parallel resonance, all you have to know, the equations and all. Okay, so now we are going to discuss a new session, which is nothing but harmonics and its effect. Harmonics and its effect. Harmonics and its effects. Harmonic and its effects. Its effects. So basically we have to know what is a harmonics means. What are harmonics? What are harmonics? In AC generator, I think you have an idea about what is an AC generator means. Synchronous generator, synchronous generator. So in a synchronous generator, normally we are designing the alternator to provide or to give a particular output frequency. Say it is 50 Hertz. The output voltage frequency is 50 Hertz. Say it is 50 Hertz. But due to many reasons, maybe the winding imperfection, or maybe the what I say exactly, the troubles in the power system. Okay, due to many reasons, due to continuous switching operation and due to continuous on and off of induction, large induction motors or transformers. So due to this, or sometime due to lightning, so there is a possibility of producing some waves which are not good for us actually, which is a multiple of the fundamental frequency. Which is the multiples of the fundamental frequency. Say it to be the fundamental frequency, 50 Hertz is our fundamental frequency. But many waves are there due to many reasons. So these are some reasons I already told you, but many reasons there is a chance of producing some waves which not good for us actually. They will produce some waves, and that wave having a frequency need not be 50 Hertz. It may be the multiples of 50 Hertz. Say it may be 2 into 50 sometime, it may be 3 into 50 sometime, it may be 15 into 50 sometime, like that. Okay, anything. So there are waves which are multiples of the fundamental frequency is called the harmonics waves. Is called the harmonics. So harmonics are what unpredicted waves arise in a power system or arise in a system, and they may harm us in different manner. Harm us in the sense harm the system in different manner. Okay. And let's see what are the effect of these harmonics on certain values or certain parameters. Okay. So I am going to tell you what is the first one, effect of harmonics on impedance. Effect of harmonics on impedance. Suppose a system is represented by some value of Z, which is nothing but Z is equal to R plus J into X. Suppose a system is represented by its impedance as Z is equal to R plus Jx. If this is for actually Z is equal to R plus Jx for the fundamental frequency. That is nothing but The frequency at which we designed the parameters, the frequency at which we designed the system, we designed the parameter, we designed the impedance, that is called the fundamental frequency. That is our area of concern, right? Say it is 50 hertz is the fundamental frequency, because all the machines, all the equipments, all the what system is designed according to that frequency. That is why it is called the fundamental frequency. Say it to be F. Say it to be F. If you have a harmonic signal which is inbuilt or which is arise due to some reasons, then I can say that the impedance due to third harmonics, say it to be third harmonics, will be equal to Z dash will be equal to R plus J into 3x. R plus J into 3x. R plus J into 3x. And similarly, the impedance due to fifth harmonics will be Z dash will be equal to R plus J into 5 into x. Which means whenever we increasing the order of the harmonics, similar manner the effect will be in the J terms, J 3x, J 5x, like that. Suppose you have to find the impedance corresponding to the 11th harmonics, means what it be? It will be R plus J into 11 times x. That means the effect of harmonics doesn't affect this R, but it affects what? It affects what? The x term. That is the reactance term. So that is the effect of harmonics on impedance. So in the question, suppose in the question, see, let's take an example. If you have an impedance of Z is equal to 3 plus J4 for 50 hertz frequency, say it to be 50 hertz frequency, then what is the value of Z for third harmonic? What is the value of Z for third harmonics? This is an example. In a one word question, this type of question may be also there, right? In a one word type answer, one word type question, no? So we have Z is equal to what? 3 plus J4. So we have to find Z for third harmonics. Let it be Z3. I am representing like it's my wish, no? So Z3, third harmonics. So it will be equal to 3 plus J into 4 into what? 3. It will be equal to what? 3 plus J 12. See the difference? So there is no changing the real part, but the imaginary part changed by multiple of that harmonic wave. Third harmonic means 3 times, fifth harmonics means 5 times, etc. So that is the effect of harmonics on impedance. This is very, very important, because one word questions, no, you may expect this type of question. One word question, no? So anything they can ask. Okay, that's right. And next we have to see effect of harmonics on speed. Effect of harmonics on speed. Effect of harmonics on speed. Let a machine is operating with a base speed or rated speed or base speed, anything you can say, equal to capital N, base speed of capital N. Suppose there is a possibility, or suppose there are some harmonics and we have to find, the speed of motor or machine, or speed of motor corresponding to third harmonics, say it to be third harmonics, will be n by 3. Clear? That means suppose the base speed n is equal to, say the machine is operating at 1500 rpm. No, it is an ideal speed, no? So 1500 rpm the machine is operating. Suppose there are some influence of third harmonics, means that harmonics will try the machine, to run at a speed of 1500 by 3, which is nothing but 500 rpm. So this is the effect of harmonics on speed. So if you have nth harmonics, then it will be what, say it will be nth harmonics, it will be capital N by small n. The speed will be capital N by small n. So by will be the result, by times that harmonics, by times that harmonics will be the resultant speed. In the case of impedance, it will affect in the imaginary part. In the case of what, speed, it will affect directly by divided by. Third harmonics mean by 3, fifth harmonics mean by 5, seventh harmonics means by 7, etc., etc., etc. Is it clear? And next we have to see effect of harmonics on frequency. Suppose a machine is operating at a base frequency of base or fundamental frequency, equal to f, equal to, let be f, then frequency of third harmonic will be equal to 3f. Clear? Frequency of fifth harmonics will be 5f. That means the frequency of nth harmonic, generally we can say that it will be n into f. Very important. That means you have to multiply that much times the fundamental frequency in order to get the frequency corresponding to particular harmonics bus. Clear? So if a machine is running at a frequency, or if a generator is producing a fundamental frequency of 50, I have already told you this thing, and if you have to find out the effect of the harmonic, third harmonics, let be third harmonics will affect the machines to produce a waveform or a cycle or a waveform of what, 150 hertz. This is the effect of third harmonics. That means along with the fundamental waveform, there are the waves of 3 times multiplication of the fundamental wave, 5th multiplication of fundamental wave, 7th multiplication, 9th multiplication, 11th multiplication, etc., etc. Clear? In which 3rd, 5th, 7th are very danger harmonics, very danger harmonics. So that we will discuss very detail in machines and all. Okay, so this is just an introduction. Okay, if you are facing a problem in one word and like that, no, you can easily solve. Okay. So that's all about the harmonics. Okay, simple thing about harmonics. Actually, harmonics is a very big topic. We will discuss in power system or machines. Okay. As of now, it's enough. Okay. And we are going to move another session. That is nothing but three-phase system. First of all, we have to see what is the meaning of balanced three-phase supply. What is the meaning of balanced three-phase supply? Suppose a supply is said to be. Balanced means, let be, three-phase means there will be 3 phases, right? We represent phases by VR, VY and VB, right? VR, VY and VB, right? If it is said to be a balanced voltage, if it is said to be a balanced three-phase voltage, the condition is that the magnitude of VR will be equal to magnitude of VY equal to magnitude of VB. That means magnitude of VR, magnitude of VY and magnitude of VB will be equal, and the phase angle between VR and VY will be 120 degree. The phase angle between VY and VB will be 120 degree, and the phase angle between R and B will be again 120 degree. That means there is 120 degree phase difference between adjacent waves or adjacent phases, adjacent voltages. Then we can say that it's a balanced three-phase supply. And one more thing you have to note here is that not only the voltages, the impedance in each phase. That means suppose it is considered to be a generator. Suppose we consider it as a generator. In the case of a generator, see, this is the generator, right? This is generator, right? This is a generator, right? Here it is producing VR, and here we will produce VY, and here we will produce VB. Suppose it is a generator, means the impedance, right? The impedance or the generator impedance, but also the load impedance. Generator impedance, also this load. Load is nothing but connected across here, right? Connected across here. That is called the load. Anything which is connected across the terminals is marked as the load. So these all are load, right? These are load. This is load. This is load, and these also load. Load is nothing but the current absorbing element which is connected across any two terminal of the generator is called the load. Okay. So suppose this is the system, this is the generator, okay, which is producing electricity. If it is a balanced system, means the load should be equal. That means across R and YB say to be 50 ohm load, across Y and B also 50 volts, across these also be 50 ohm. That means the impedance corresponding to each branches will be, let be ZR will be equal to ZY, let be equal to ZB. That is the impedance or per phase impedance of each branch will be, or each phase will be same magnitude, not the that complete complex form, but the magnitude should be equal. That is the meaning of a balanced three-phase supply. And also if there are currents, if there are voltage, mean due to that there will be, of course there will be current. The current waveform also follow this pattern. Current waveform, there will be R phase and let be Y phase and there will be V phase. The current waveform also there will be IR and there will be IY and let be IB. The currents also follow the same pattern. That pattern is nothing but between 120 degree, between 120 degree, between 120 degree. This also follows the same pattern. That means the 120 degree between the adjacent phase currents. Is it clear? And we can say that suppose normally we take this R is the reference vector, the reference phasor. So I can say that IR will be equal to Im sin omega, which is sin omega t, which is nothing but the sinusoidal voltage. We know the general equation for sinusoidal voltage is nothing but Im sin omega t, right? Then Iy will be equal to Im sin omega t minus 120 degree, and Ib will be equal to what? Im sin of omega t minus 240 degree. That is 120 minus 120 again, which is nothing but 240. If this equation satisfy this IR, IY, and B satisfy this condition, then we can say that this is a balanced supply. This is a balanced supply. This is a balanced supply. That's all about the balanced supply. Is it clear? So balanced is nothing but there should be 120 degree phase difference between each of the phases, Also the impedance across the phases will be equal, magnitude of the impedance will be equal, and there are the magnitude of VR, Vy and Vb will be same, and also we can say that the magnitude of IR will be equal to magnitude of Iy will be equal to magnitude of Ib. Magnitude of Ib. That also we can say. The magnitudes are same, but the instantaneous value, no, it will be very differently. It will be very different. Then I will ask you a question. I will ask you a question. You know, birds are sitting on three-phase line, right? Birds are sitting on three-phase line, right? Birds are sitting on three-phase line. Three-phase mean let be R, let be Y, and let be B. Okay. Of course, there will be VR, Vy, and Vb. Each line having certain voltages, VR, Vy, Vb, let be. And I already told you that if it is a balanced system means what happens, this VR will be equal to Vy, Vb equal to Vb. Okay. Suppose a bird is sitting here and its two legs are connected across this R and Y. Whether it get a shock or not. Whether that bird get a shock or not. That's my question. Whether that bird get a shock or not. Because it is a balanced supply, no? So VR will be equal to definitely Vy. VR will be definitely equal to Vy. Whether that a bird will affected by shock or not. What is your answer? The answer is prima facie, no, you may feel that VR equal to Vy equal to Vb means both are same voltages, that means there is no potential difference, so that there will not be any current, because only there is a potential difference, there will be a flow of current, right? There is no potential difference, there will not be any flow of current, so the bird will not get any shock. That may be your answer sometime, but the answer is not. The bird definitely get a shock. Why? Why? Because even though the magnitude of current are same, or even though the magnitude of voltages are same, the same will be applicable for this also. VR equal to Vm sin omega t, Vy is equal to Vm sin of omega t minus 120, and Vb is equal to Vm sin of omega t minus 240. This is also right. This is also called balanced, right? This is also called balanced supply. But even though the magnitude of VR will be equal to V by equal to Vb, but the instantaneous value is not same. In one it is simply omega t, in another one it is omega t minus 120, in another it is omega t minus 240. That means if you are trying to draw the three phases in a graph, see, in a graph, suppose this is R phase, let be VR, and after 120 degree one phase is, this is 90 and this is 120, right? And this is 120, okay, and after that it's emerging, so I can say that this is Vy, and again after 240 degree another wave is emerging, right? So this is 180, right? 180, this is 90 of course, this is 90 of course, this is 60, right? So possibly this may be the voltage waveform. So this is the Vb, this is Vb. So this is the waveform, this is the three-phase waveform. So even though the magnitude of VR, Vy, Vb will be same, but the instantaneous value will not be same. Instantaneous value will not be same. Clear? That means suppose a wave is at a maximum at this R phase is maximum at this point, means the Y phase is not maximum. This is somewhat not in a minimum. And again the phase, this Y is not Vy and Vb no Vb. Again it is negative, again increasing on negative side. That means if you take at any instant, the three phases are not equal. Three phases are not equal. That means any instant of time, the instantaneous value of the three phases are vary or different. Since the instantaneous value is different, there is always some phase, potential difference. Because VR is instantaneous value, VR not equal to Vy, not equal to Vb. So when a bird touches, it is two legs on two phases on a balanced three-phase supply. That two legs are not in the same potential. That two are in different potential. So definitely the bird will affected by shock, or definitely the bird will get a shock and die. Is it clear? That is one interesting question regarding the balanced three-phase supply. So balanced supply is nothing but there should be 120-degree phase angle between corresponding phases, and three phases are there definitely, and the per phase impedance is same. Per phase impedance is same. And the magnitude of VR, Vy, Vy will be same, and the currents also same. Okay. And let's say what is, I think you already heard this term, phase sequence. Phase sequence. Phase sequence. Phase sequence means, see, suppose I have three phases, let be VR and Vy, and will be Vb. If I am rotating this phaser, or phase sequence is nothing but, the definition of phase sequence is nothing but the order in which each phase attains its maximum, that is called the phase sequence. So the definition of phase sequence is nothing but the order in which phases attains its maximum value. Phases attain its maximum value. That is the meaning of phase sequence. I will explain the term. The order in which the phase attains maximum value means, suppose in a phase sequence, suppose I already told you that see this wave, first we produce a waveform corresponding to R phase, let be VR, that means the first wave attains its maximum first, right? This wave attains its maximum first, and the second wave is nothing but Vy now, which is produced 120 degree after this first wave, 120 degree after the first wave. That is the Vy. This is 120 degree, of course, this is 120 degree. This is Vy. That means this wave attains its maximum after this wave attains the maximum, right? After R wave attained the maximum value, only Y wave going to attain its maximum. And again, this is 180 and this is 60, 240. And after the V wave attained the maximum, only that phaser or phase Vb attained its maximum. Vb attained its maximum. That means positive maximum, correct? So the order in which it attains its maximum is termed as phase sequence. The order in which, whether R phase is attaining maximum, or whether sometimes, no, these generators are our design. So sometimes instead of R phase, Y phase may attain its maximum. We are designing in such a manner. We can design that also. We are producing a Y phase first, and that Y phase will cut the magnetic field first, and it will produce the maximum value. So sometimes that also may happen, no? So the order in which the phases attain its maximum, whether the first wave emerging is R, whether the first wave emerging is Y, whether the first wave emerging is B, that is called the phase sequence. Clear? So there are two phase sequence. First is nothing but positive sequence. I will explain that. Positive phase sequence. First is positive phase sequence. Positive phase sequence means if the vectors are rotating in anti-clockwise direction, so we can say that positive phase sequence means what? if the phasors or the voltages or the current, normally this is called phasors. If the phasors are rotating in anti-clockwise direction, then it is called the positive phase sequence. Okay, that means I will explain. Suppose I am taking R as a reference, no? R as a reference. So let be R as a reference. If I turn Y in anti-clockwise direction, it will have a position of R right now. This is R, right? So if I rotate this Y, or I rotate simply 120 degree towards anti-clockwise direction, then this Y will attain the same position as that of R. So there will be Y. This Y will come here, right? So R, Y, and again it will be what? Again I shifted it to again 120, it means this VB will come here, right? So it will be RYB. So RYB will be the phase sequence of this positive sequence. That means, suppose you ask what is the phase sequence here, means RYB you can say a phase sequence, or you can say YB are also a phase sequence, positive phase sequence, or you can say B R Y also a phase sequence, positive phase sequence. So positive phase sequence is nothing but, if you take a reference vector, suppose VR is the reference vector, try to turn other vectors in anti-clockwise direction and write on the back of that vectors. Bus. Suppose R I take, so back is nothing but Y in anti-clockwise direction. Again we shifted in the anti-clockwise direction, it will have B. It will have B, no? Suppose you took Y as a reference, first vector Y. If you turn this, if you turn the beside, back vector in anti-clockwise direction once, this will attain here. So it will be YB. Once more, if you turn the phasors or vectors in anti-clockwise direction, this R will come here, right? That means R. So YBR. Or if you take the reference vector as B, the back vector or the anti-clock, when the back vector rotate in anti-clockwise direction, that will be what VR will come here. So it will be R, and when you turn once more anti-clockwise direction, this VY comes here and it will be VRY. Is it clear? Is it clear? So that is the meaning of positive phase sequence. Another phase sequence is, so I can say that this is nothing but anti-clockwise direction. So positive phase sequence is nothing, it's a reference phase sequence actually. Generators are normally rotating anti-clockwise direction and motor are rotating in clockwise direction. Okay. Normally generators are rotating anti-clockwise direction. So that positive phase sequence is nothing but the base phase sequence or generator phase sequence. So another phase sequence is also called, it is called the negative phase sequence. I will explain. Negative phase sequence. I will explain what is this. Another phase sequence is also called negative. Another phase sequence is called a negative phase sequence. Okay. The meaning of negative phase sequence means the vectors or the phasors are rotating in clockwise direction. The vectors are rotating clockwise direction. That means, suppose you take the reference vector as R. If you turn this vector in positive clockwise direction, what happens means, if you turn this in positive clockwise direction, this B will come back to the R, right? This BV will come back to the position of this R, right? If you turn this is in clockwise direction, positive 120, clockwise 120 degree rotation. If you turn this vector in clockwise 120 degree rotation, what happens? This VB will come here, right? That means this VB will attain a position of R, right? So this will be B, and again you turn, it will be Y. So negative positive phase sequence is one, RBY is a negative phase sequence. Another one, suppose you take Y as the reference, right? Y as the reference, right? Y, if you turn this Y in positive direction, 120 degree positive in clockwise direction, what happened? This VR will come here, right? This VR will come here. That means R, and again you turn once more, this VB will come here, right? So B. Suppose you take VB as a reference, so I can write it will be B as the reference, B as a reference. What happened? If you turn this VB in 120 degree clockwise direction, what happened? This VB will come here and this VB will come back to this VB, right? So it will be Y back. That means first B back of that it will be a Y, and again back of that it will be R. So these will be the negative phase sequences. Negative phase sequences. Is it clear? Is it clear? Is it clear? So if you have a question like this, and this is, I can say that this is in clockwise direction. So generally this negative phase sequences, I mean we are rotating the motor in a clockwise direction actually, and rotating the generator in an anti-clockwise direction. Okay, so the meaning of positive phase sequence is nothing but we have to rotate it in anti-clockwise bus. The nature of the negative phase sequence is nothing but we have to rotate the vectors or phases in what? Clockwise direction bus. So that is the only thing we have to note. That is the only thing we have to note. And another one is also, it is called zero phase sequence. Zero phase sequence is nothing but there is no phase difference between phase angle difference between R, Y, B and B. Then it is called zero sequence vectors. That is not at all important. These two are very important, positive sequence and negative sequence. Okay, so R, Y, B, Y, B, R, B, R, Y, C. Clear? Is there any terms which is similar meaning? R, Y, B is there? No. R, Y, B is there? No. Y, B is there? Y, B, R is there? No. B, R, Y is there? No. B, R, Y is there. So that is the positive and negative phase sequence. So phase sequence is nothing but the order in which it attains the maximum. So in the positive phase sequence we can say that first phase is R, next is Y and next is B. So suppose if you take Y as the reference vector, then first is Y, next will be B and next will be R. That's all. I think you already learned in your first year electrical engineering, right? First year. So that's all about the phase sequence and positive and negative phase sequence concept. Okay, what's the time now? Time is there. Okay, next we have to see we can connect the three-phase system in two different manner. That means nothing but three-phase system means there should be three phases. That means there are three phases of or three bundles of conductors. Simply, no, it's a simple language. Three bundles of conductors that will continuously cut the magnetic field, and some voltages will be generated. That is the simple meaning of what three-phase system. There are three groups of what conductors, and each are displaced by 120 degree. We know that each are displaced by 120 degree, and it will produce its own corresponding voltages, and we take it outside from the generator. Then it is called the three-phase system. It is happening in the inside generator, right? Inside the generator is happening, and we have take that to three terminals outside, and if you measure the voltage between any two terminals, there will be some voltages. That is it's called a three-phase voltage system. And we are going to deal with, I'm going to deal these three phases. No, this is, let be R phase, let be R phase, let be Y phase, and let be B phase. The three phases can be connected by two ways. That means This is a group of conductor. It should have some starting and end point. And another one is, this is the Y phase now, this is R and this is Y. It should be also having some starting phase and some ending point, and this is nothing but the B phase. It also having some starting and ending point. In order to get 3 lines as the output, then only we can say it's a 3-phase supply. If you are getting 3 lines as the output from a generator only, we can say that it's a 3-phase supply. So there are 6 terminals, 1, 2, 3, 4, 5, 6. We can't take 6 terminal as the output of a generator. Then it will be called what? Not a 3-phase supply. We just need 3 phases from the generator as its output. So that we have to connect these 6 terminals. This is terminal 1, 2, 3, 4, 5, 6. These 6 terminals now we have to connect in some manner and to produce only 3 conductors as the output of a generator. That different connections now we can connect these 6 terminals in different manner. The manner is actually 2 types. The manner in which we can connect the 6 terminals is 2 types. First one is star and second one is delta. First one is star and second one is delta. Clear? So let's see one by one. 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 First we have to see star connection. Star connection. Listen. So star connection means the similar ends of the phases, the similar ends of the conductors are connected together. That means this R phase this R phase having 2 terminal. One is R and another one is R dash. This Y phase having also 2 terminals. One is Y and another one is Y dash. The other end is Y dash. This B also having 2 terminal, one is B and another one is B dash. If you connect the common terminals, that is nothing but the starting terminals R, Y, B. R is the starting terminal of R phase, Y is the starting terminal of Y phase, B is the starting terminal of B phase. If you connect these starting terminals together and the ending terminals across which you are taking the supply, then it is called a star connection. That is means common point connected together, and that is called the neutral. Okay, so that is the meaning of star connection. And we have to see some important terms regarding the star connection. Due to this VR, there is a current IR, and the same current is come here, that is nothing but IR. Due to this V by, there is some IY, the same current is coming here, that is nothing but IB. Due to this VB, there is a current IB and the same current V is come here, that is IB. Clear? And there we are connecting loads, there we are connecting loads, or simply, for simplicity, you can take simply The voltage between R and Y is termed as VRY. Okay, VRY, and the voltage between Y and V is termed as VYB. Y and B we termed as V by V, and the voltage between R and B is termed as VRB. R and B is termed as VRB. Okay, and we have to focus two terms, that is nothing but line voltage and phase voltage, line current and phase current. Line currents and phase current. First we have to see what is the meaning of line voltage. What is the meaning of line voltage? Line voltage means it is the voltage between any two lines, not in neutral. Neutral you can't count. If line voltage means the voltage between any two lines except neutral. Okay, any two lines except neutral. That means line voltage is nothing but it may be what? VRY is a line voltage, VYB is a line voltage, and VRB is also line voltage. So line voltage is nothing but the voltage between any two lines except neutral is called the line voltage. Similar manner, line current also. Line currents means the current through any line is called the line current. The current through any, this is a line, this is a line, this is a line, except neutral again. This is a line, this is a line, this is a line, right? This is called the line current. So IR, let be I by also, let be IB also. So these are called the line quantities. And next you have to see what is phase voltage. Phase voltage. Phase voltage means the voltage between any one line and neutral is called the phase voltage. That means phase voltage means simply let be VRN or simply VYN or simply VBN. Simply VBN. So phase voltage means it is the voltage between any one phase and neutral. Any one phase and neutral. It is the voltage between any one phase and neutral. It is the voltage between any one phase and neutral. That is called the phase voltage. That is called the phase voltage. And phase current, what is phase current? What is phase current? It is nothing but the current in each phase. The current in each phase is called the phase current. What is the current in each phase? This is the R phase. The current in this phase is nothing but IR. This is the Y phase. This is the Y phase. So the current in this phase is IY. Phase means up to this, no? Up to this you can consider as a phase. So IY is the phase current. Similarly IB also. So phase currents means it is nothing but the currents in each phase is represented as phase current. And you can see or you can observe an interesting fact here is that these two are same, no? These two are same, no? That means in a star connection or balanced star connection, this is actually balanced, no? We are dealing with balanced, it is understood, no? Balanced star connection. In a balanced star connection, I can say that in a balanced star connection, line current equal to phase current, or line current is represented by IL and phase current is represented by I phase. So in a balanced three phase star connection, line current and phase current are same. That is nothing but the current which is emerged from this R phase is same as the line. It is come here and is come as same as the line. It is emerged here and it's come out as same as the line. It emerged here and come out as same as the line current. So in a balanced three-phase star connection, we can say that the line current and the phase currents are same. But we can't say that this and this not same. This and this not same. That means the line voltages and the phase voltages are not same in balanced star connection. Not same in balanced star connection. Okay. Then we have to find how much difference is there in line voltage and phase voltage. That is our next step. We learned there are some difference in line current and phase current, no? As an engineer, it is our duty to find how much difference is there, no? How much difference is in between line current and phase, line voltage and phase voltage, you have to find, no? That is our duty as an engineer, right? So we have to find. So we have to find. So we have to find. So we have to find since it is a balanced supply, let be VR and let be V by and let be VB. Okay, and I am extending this VB as, okay, this V by as minus Vy, minus V by, minus V by, minus V by, and the resultant will be what? See, when you cross this all are 120 degree, right? This is 120 degree and this is also 120 degree, right? When you cross exactly in middle of this vector Vy, we are projecting means this will be 60 degree, right? This will be also 60 degree, right? And the resultant will be like this. This is nothing but VRY, which is nothing but VR minus Vy, correct? VR minus Vy. Okay, so VR, Vy, Vb you draw, you extend this vector Vy as minus Vy, and if two vectors are acting with an angle 60 degree, you learned the parallelogram law of vector addition, right? Parallelogram law of vector addition in +2, right? If two vectors are acting in certain angle, then the resultant will be what? What will be the resultant? That is nothing but VRY will be the resultant, right? VRY or VR minus Vy, which is nothing but VR square mod VR square plus mod Vy square plus 2 into mod VR mod Vy into cosine of the angle between VR and Vy, which is nothing but 60 degree. Correct or wrong, beta? Correct or wrong? This is called the parallelogram law of vector addition. If two vectors R and Y are acting in some angle which is nothing but 60 degree, then the resultant vector will be, the resultant value of vector will be VR square, first one magnitude square plus second one magnitude square plus 2 into first one magnitude into second one magnitude, the cosine of the angle between these two vectors. That is nothing but 60. That is nothing but 60. So that what is VRY? It is line or phase? VRY, it is line or phase? It is nothing but line. It is nothing but line. It is equal to root of what is VR? It is line or phase? VRN or simply VR? It is line or phase? It is phase. VY, it is line or phase? It is also phase. 2 into VR, it is phase. Vy, it is phase. What is cos 60? 1 by 2, 2 and 2 get cancelled. So it will be root of V phase square plus V phase square plus again V phase square, which is nothing but root of 3 V phase square. Or I can say that VL will be root 3 into V phase, simple. Simple. Katam Kali. Katam Kali. Is it clear? Is it clear? That means in a balanced star phase or star connected system, the line voltage will be root 3 times higher than the phase voltage. That is the difference. We already learned that there is some difference between line voltage and phase voltages, right? So what is the difference? This is the difference, bus. What is the difference? This is the difference. There is the line voltage will be root 3 times higher than that of the phase voltage beta. It is 1.73, right? 1.7173, right? So that much time higher than the phase voltage is the line voltage. Is it okay with you? Is it clear? The concept is clear to you, beta. The concept is clear to you, beta. Okay. So that is the concept of star connection. That is the concept of star connection. Next we have to see delta connection. The another connection of three-phase system. The another connection of three-phase system is nothing but delta connection. Delta connection. See the peculiarity of delta connection. So delta connection is nothing but, see, consider the phase R. This is R phase now. It having a starting terminal R and a ending terminal R dash. This is Y phase now. This is also having a starting terminal Y and ending terminal Y1. This is B phase now. This is also having a starting terminal B and ending terminal B dash. What we are doing in a delta connection? In a delta connection, the dissimilar ends connected together. It's very, very, very important. That means the starting terminal of one phase is connected to the finishing terminal of other coil. The starting terminal of one phase is connected to the finishing terminal of other coil. The starting terminal of one phase is connected to the finishing terminal of other coil. That type of connection is called delta connection. In this manner we can also get three phases out as output. Our aim is what? We have to take only 3 terminals from the 6 ends, right? There are 6 ends are there for 3 conductors, right? Each conductor there are 2 ends, right? So total there are 6 ends. We don't need that 6 ends together as an output. We only need 3 terminal as the output. We only need 3 terminal as an output. That means we have to suitably connect the 6 terminals together and produce effectively as 3 terminals. That is our aim in star or in delta connection. Bas. So in delta connection what we are going to do is, we are connecting the starting terminal of one is connected to the finishing terminal of other. Starting terminal of one is connected to the finishing terminal of other. Likewise. Here also, this is VR, right? So definitely there will be current now, let be IR. This is Vy raise, definitely there will be current now, there will be Iy, and this is Vy knee, definitely there will be a current, let be Ib, let be Ib, right? Let be Ib, right? This Ib, both simultaneously you can take in a similar manner, right? Similar manner, because this is you take in anti-clockwise, this is you take in anti-clockwise, so these also you should take in anti-clockwise. Otherwise, no. Assuming you can assume in any manner, but in similar manner you can assume, right? Similar assumption will be there. This IR is in anti-clockwise, Iy is in anti-clockwise, this Ib is in also. That is the way you can assume. Okay. So these are the currents. So there will be of course some voltages, right? So this is V R Y, right? And this is V Y B, right? Correct? And this is V R This is VR. No, 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 no. Simply VR, simply VB. Okay. See, and this is current is nothing but IR minus IB. I will explain, okay? Don't worry. This is nothing but, and this is nothing but, okay, I will explain. So this is the connection of star connection. This is the phase R, right? This is one phase R, right? Due to this there is a current in R phase which is nothing but IR. This is a Y phase, due to which there is a current IY. This is B phase, due to which there is a current IB. Both, I mean all will be taken in an anti-clockwise direction because we are assuming in similar manner. That's the concept. And this is a junction, right? This is a junction, right? This terminal can carry a current of the difference between these two. That is nothing but you can apply KCL here, current Kirchhoff current law here. That is means the incoming current minus the outgoing current will be the resultant current here, right? The third terminal current or the current through this line will be equal to what? The incoming current minus outgoing current will be the total current here. That then only the algebra sum of current in this junction will be 0, right? If we add this current IR minus IB, IR and IB, then it will be 0, right? Because the incoming current will be taken to be positive and outgoing current to be taken to be negative. If we add together, you will get 0, right? So in simple manner, the third line current will be nothing but the incoming current minus the outgoing current. Incoming current is taken to be plus, that is IR. Outgoing current is taken to be minus, that is IB. Is it clear? And consider this junction also. The incoming current here is IY, the outgoing current is IR, so IY minus IR. Considering this junction also, the incoming current here is what? IB, right? The incoming current here is IB and the outgoing current here is nothing but IB, so it will be IB minus IB. That is the current directions. That is the current direction. So you can see from here that, okay. And see, what about phases, right? This is VR phase, right? R phase, right? Definitely there will be some voltage, no? The same voltage will be available here also, right? That means across R and B, R and Y, you can feel the same voltage VR because this is exactly taken to this side, that is VR. Same voltage will be available here. And this is VY, no? If you connect these two terminals means you can feel the same voltage here also, that is VY. And this is nothing but VB, no? If you connect these two terminals across these and these, definitely the voltage between these two will be equal to VB. Correct or wrong? Simply, parallel connection voltage will be same. That is the concept. That means in a delta connection, the line voltage and phase voltages are same. Correct or not? Line voltage is nothing but the voltage between any two lines. That is the line voltage is nothing but VR, right? And actually it is VRB, but VRB is equal to what? VR. VRB is nothing but it is equal to simply VR because it is parallel. Same point is there, so it will be VR itself. And we can say that in a delta connection, the line voltage and phase voltage are same, but see, this is the phase current IR. Is the same that of the line current? No. So in a delta connection, the line current and phase current not equal. The line current and phase current not equal. So our aim is to find how much this line current and phase currents differs. How much times this line current and phase current differs. That is our aim. Okay. So we have to find the relationship between line current and phase current, no? So definitely our phasor diagram will be what? In terms of current, right? So it is a balanced three-phase supply, no? So this will be IR and this will be IY and this will be IB. Both having 120 degree phase angle. There is no doubt in that. 120 degree. Clear? So I am extending this IY like this and this is I minus Iy, and this will be the resultant. This will be the resultant. IR minus Iy. IR minus Iy or Iy minus Ry, anything you can take. IR minus Ib. Okay, for simplicity now, you might be confused, right? So let's take like this. Let us take this. No confusion. We don't need to confuse any manner. See, this is IR minus Ib, no? So you have to extrapolate or extend the vector Ib like this. Ib like this. So it will be no minus Ib. So resultant will be IR minus Ib. Simple beta, simple. IR minus Ib. And this is nothing but the angle between these two will be what? 60 degree. Correct or wrong, beta? Correct or wrong? 60 degree. So I can say that vectors, I mean the resultant IR minus Ib, which is equal to, again applying parallelogram of law of vector addition, it will be equal to mod IR square plus mod Ib square plus 2 into mod IR mod Ib beta mod IBR mod Ib cos 60. Correct or wrong, beta? Correct or wrong? That will be equal to IR minus Ib is nothing but, see, IR minus Ib is nothing but line current, right? Line current, because it is a line current. External to the generator is all lines, right? So it is a line current. So I can say that is a line current. IL equal to, what is IR? IR here it is phase current, right? So it will be I phase square plus I phase square plus 2 into I phase into again I phase into 1 by 2, because cos 60 is nothing but 1 by 2. So it will be again equal to IL is equal to root of 3 I phase square, or I can say that IL is equal to root 3 times I phase. IL is equal to root 3 times I phase. So this much difference is there in delta connected system, that too for currents, line current and phase current. So line current will be root 3 times the phase current. Bas. So did you get the idea of how can we take the line quantity and how can we take the phase quantity, right? So line is nothing but any two lines, phase is nothing but between one phase and neutral. Normally neutral voltage is to be 0, right? Normal voltage is to be 0, right? That's why it is not mentioned properly. That is, sometimes it may be VRN, simply sometimes it may be VR only. Sometimes it may be VYN, sometimes it's simply VY. It is understood both are same, right? Both are same, right? That means in a balanced 3-phase system, we will prove that also. We will prove that also. So we have a question. What is the neutral current and voltage in a balanced 3-phase supply? Balanced 3-phase. This is the question actually. What is the neutral current and voltage in a balanced 3-phase system or supply? See, we know that whether in a balanced 3-phase system, the voltage or current follow a relationship. Let be IR equal to, what is that? Im sin omega t. Iy is equal to Im sin of omega t minus 120 degree, and Ib is equal to Im sin of minus 240 degree. If you add this 3, let be 1, let be 2 and let be 3. If you add this 3, that is nothing but the neutral current In is nothing but, if you have a balanced supply, see, this is the balance, right? Let be IR and let be Iy and let be Ib, and the neutral current will be this in this direction, In. Because for every conductor, neutral is acting as the return conductor, right? So for every conductor, neutral is acting as the return conductor. That's why all are outward but neutral is inward. That means neutral current will be nothing but the sum of IR plus IY plus IB. Correct or wrong, beta? Correct or wrong? IR plus IY plus IB will be the neutral current in a balanced 3-phase supply. So here it will be nothing but IN will be equal to Im sin of omega t plus Im sin of omega t minus 120 degree plus Im sin of omega t minus 240 degree. By using simple trigonometry relation, sin A minus B is equal to sin A cos B minus cos A sin B. Sin A minus B is equal to sin A cos B minus cos A sin B. And you do for this and you simplify this, you will get definitely 0 ampere. In is equal to 0 ampere. And if you go for similar manner, VR is equal to Vm sin omega t and Vy is equal to Vm sin of omega t minus 120 and Vb is equal to Vm sin of omega t minus 240 degree. Then also the neutral voltage you will get as the sum of Vr plus Vy plus Vb, which is nothing but 0 volt. That means neutral line is called as neutral line. Neutral line having 0 current, 0 voltage. That is why this neutral line is also called zero power bus. That is why this neutral line is also called zero power loss, because power is nothing is voltage into current. V into I will be equal to what? 0, 0, 0. That's why this neutral is called what? Zero power bus. That's it. So in a balanced 3-phase supply, the current in a neutral conductor is nothing but 0. The voltage in a neutral conductor is nothing but 0. Simple. Okay. So that's all for today. So let's meet tomorrow with new sessions and some problems. Okay. So bye. Take care.